In this lecture, we'll discuss why it's so difficult to learn about extrasolar planets and how a star's motion or changes in its brightness can reveal the presence of planets. Our Milky Way galaxy has over 200 billion stars. Even if only a small fraction of those stars have planets, our galaxy should still be bursting at the seams with planets. Current theories of star formation predict that planetary systems are a natural consequence of the process. Therefore, planets shouldn't be rare at all. But it wasn't until the 1990s that we began finding these planets. The simple reason being that detecting extrasolar planets is a technical challenge. Why the difficulty? Well, first, the stars are very far away. Even if we are looking around the nearest stars, it's like being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. It's not so easy. The second challenge is how bright the stars are compared to their planets. A sun-like star is a billion times brighter than the light reflected from any of its planets, so imaging a planet next to a distant star is also quite difficult. But human ingenuity has prevailed, and we've come up with clever ways to look for extrasolar planets despite the challenges. We look for planets in two general ways, directly and indirectly. Direct detection means obtaining actual images or spectra of the planets, and indirect detection means inferring the existence of the planets without actually seeing them. We'll talk about indirect detection first. Under the indirect umbrella, there are two major approaches to finding and studying extrasolar planets. First, we can observe the motion of a star to detect the tiny gravitational effects of the orbiting planets. And second, we can observe changes in a star's brightness that occur when one of its planets passes in front of the star. The first indirect approach, the gravitational one, is possible because stars and their planets orbit around a common center of mass. We usually think of one object orbiting another object, like the Earth orbiting the Sun, but objects attracted by gravity actually both orbit around their common center of mass. For example, in a binary star system in which both stars have the same mass, we would see both stars tracing ellipses around a point halfway between them. When one object is more massive than the other, the center of mass lies closer to the more massive object. The idea that objects orbit their common center of mass holds even for the Sun and planets. It's just that the Sun is so much more massive than the planets, so that the center of mass between the Sun and any planet actually lies inside the Sun. Consider a star and a single planet. The star is still orbiting around the planet, even if the center of mass is inside of it, and the planet is still orbiting around the star. Also, the orbital period of the star is the same as that of the planet. The Sun's system is more complicated than just one planet. The Sun is orbiting around the combination of all the planets and everything else in the solar system. If we were an alien species watching the solar system from a distance, we'd see the Sun wobble. And if we were really careful with our measurements and if we knew a little physics, we'd be able to figure out there are multiple planets orbiting around the Sun. To find planets around other stars, we need to therefore look for the motion of the star caused by the gravitational tug of its planets. We can look for this motion by making precise measurements of the star's position in the sky. This is called astrometry. Or we can measure the changes in the star's velocity toward or away from us using the Doppler effect. Let's consider astrometry. This is not an easy measurement to make. For example, a Jupiter-sized planet orbiting 5 astronomical units from a Sun-like star would cause its star to move only about 0.003 of an arcsecond. This is approximately the width of a hair seen from 5 kilometers. Very tiny. But it's not undoable. The European Space Agency's Gaia mission has already launched and is in the testing and calibration phases. It will measure positions of a billion stars in our galaxy, some to an accuracy on the order of micro arcseconds. The Doppler technique also looks for gravitational tugs of planets around stars. You may recall the Doppler effect allows us to measure the velocity of a star toward or away from us. When the star is moving toward us, the light is blue shifted. When the star is moving away from us, the light is red shifted. This technique can measure motions as small as 1 meter per second, basically walking speed. The Doppler method was used for the first discovery of an extrasolar planet around a sun-like star in 1995. The Doppler shift of the star 51 Pegasi indirectly revealed a planet with a 4-day orbital period. This short period means that the planet orbits very close to the star, about 1/8 of Mercury's orbital distance from the Sun. This figure is an artist's impression of 51 Pegasi and its planet. At distances so close, the planet must be very hot. In fact, the planet orbiting 51 Pegasi is an example of what is known as a hot Jupiter, a planet with a Jupiter-like mass but a much higher surface temperature. This is what the data look like for the Doppler method. This is a plot of the star's radial velocity over time. When the velocity is positive, the star is moving away from us. When the velocity is negative, the star is moving toward us and the light is blue shifted. At the beginning of the plot, the velocity is positive and the star is moving away from us. As soon as it crosses the zero, the velocity is negative and the star is moving toward us. Again, when it crosses the zero, the velocity is positive and the star is moving away from us. This pattern will repeat as the planet orbits around the star and the star wobbles. Remember, this plot is the radial velocity of the star and not of the planet. The second general method of detecting planets indirectly is called the transit method. If a star system is lined up so that we are seeing it edge on, then one or more of its planets will pass directly between us and the star once each orbit. The result is a transit. The eclipse reduces the star's apparent brightness and can tell us something about the planet's radius. Because most stars exhibit some intrinsic variations in brightness, we can be confident that we have detected a planet only if we observe the dips in brightness to repeat regularly. The period of the repeated dimmings tells us the orbital period of the transiting planet. The goal of the Kepler mission is to discover Earth-like planets in Earth-like orbits, worlds that could potentially have life. This is a technically challenging goal, but Kepler has been enormously successful, finding nearly 3,000 planet candidates, some of which are in that habitable zone. Finally, this is a table from the text summarizing the advantages and limitations of the indirect methods I just talked about. I don't want to spend a lot of time here. You can have a look-see for yourself at the different techniques and the progress we've made so far with planet detection. That's it for now. I'll talk to you more about extrasolar planets soon.